Describe the concept of inertia. Inertia is a body's resistance to its change in state of motion. You need to get quite a lot of those concepts around. It's a resistance. It doesn't have a unit or anything. It is an idea. So it is a resistance, and it's to state of motion. Because state of motion is either if it's standing still, it doesn't want to change, or if it's moving at a certain velocity, it doesn't want to change. Then what have we got? We've got this bullet that's just come out the gun. It's got a weight, and most of you did this really well, thank you. And then it obviously encounters some air friction. And that's it. And you are very good about not putting in some little man who's running through the air, pushing it from behind. Excellent. Now we've got a 700-gram block. We better change that into 0.7 kilograms. And we've got a coefficient of static friction. We are on a horizontal surface, so we don't have to worry about any causes or signs or components or anything. We just want the frictional force. Frictional force is equal to mu force normal, and the force normal is mass times gravitational acceleration when you are on a horizontal surface. 0.26, 0.7, 9.8, and your answer comes out to 1.78 newtons. State Newton's second law of motion. You've got to actually learn these definitions particularly well. And we're going to land up. If a force acts on a body, that body will accelerate. That's mark number 1. The acceleration will be directly proportional to the net force. That's mark number 2. And inversely proportional to the mass of the body. Mark number 3. Please check your definitions carefully. Now we have an inclined plane. So, if we have an inclined plane and we've got an 18 kilogram body on there, we know that we need to first find the weight, and then it's going to be 176.4 newtons. That's the 18 times 9.8. So that's just weight. We've been told it's at an angle of 34 degrees, which means that when I'm working out the components, this angle over here is going to be, let's just make this a little bit bigger, is going to be 34 degrees. There we go. And now we need to work out the vertical and the horizontal component. This is the adjacent side, so it's 176.4 cos of 34 degrees, and that turns out to be equal to 146.24 newtons. Then we have to work out the opposite side, so it's 176.4 sine of 34 degrees, and that's going to be equal to 98.64 newtons. Now we need to work out the frictional force, and the frictional force is going to be up the slope, and frictional force is always equal to mu times force normal. Mu, they tell me, is 0.15, and the normal force is going to be exactly equal to that pink force over there, which is the component of weight that is into the plane, and it is 146.24. So I get a frictional force of 21.94 newtons. Therefore, what is the force resultant on this body? Force resultant is equal to the big force down the plane, which is going to be 98.64, minus the small force up the plane, 21.94, and I land up with 76.7 newtons. That is equal to mass times acceleration, which is 18 kilograms times an acceleration that I don't know is 76.7 newtons, and therefore the acceleration is 4.26 meters per second squared. The final part of that question is we need to work out how long it would take to get to a speed of 6 meters per second. So how are we going to do that? We're going to say final velocity is 6, initial velocity is 0, acceleration is 4.2, and I'm going to work out how long will that take. So I was given a final velocity, I know it started from rest, I've worked out an acceleration, now I can easily work out the time, and the time turns out to be 1.4 seconds. state Newton's third law. I must warn you, Newton's laws, they love to ask them in exams, which is why I've put quite a lot of them into the test. You can't just say for every action there's an equal but opposite reaction. You need to say for every action force there's an equal but opposite reaction force. Or if body A exerts a force on body B will exert an equal but opposite force onto body A. But you must get these laws of motion correct. Mark standing on a Newton calibrated scale in a lift, his mass is 85 kilograms. So if his mass is 85 kilograms, we can work out his weight. His weight is equal to mass times gravitational acceleration, which is going to be 85 times 9,8. Let's just think about it. The lift is accelerating upwards. If you think about a lift going up, you feel heavier. So we're going to add onto that the total force on the scale, which is going to have an extra mass times acceleration, which is 85 times 0.75 meters per second squared. Just to clarify and to actually give you the science, not just that you feel heavier, but what happens is as the lift pushes up onto the person, it's accelerating upwards, the person pushes downwards onto the lift, and therefore it adds some extra force downwards onto the lift, onto the scale, and you get 896,75 newtons. Two blocks with masses of 3 kilograms and 7 kilograms respectively are joined by a piece of light string. So we have to draw each of those. We've got a 3 kilogram, we've got a 7 kilogram. The 3 kilogram has a horizontal force of 15 newtons. They're connected. There's obviously tension there and tension there. So force resultant is equal to big force, tension, minus small force, 0. 7A is equal to the tension. Here, force resultant is equal to the big force, 15 newtons, minus the small force tension. 3A is equal to 15 minus, I know the tension is 7A, so I'm going to pop that in there. 10A is equal to 15, and A is equal to 1,5 meters per second squared. In the direction, acceleration is a vector quantity, in direction of applied force. You had to draw the two, let's see what we were asked to do, draw two separate force diagrams. So we needed to write the words in here. This would have applied force, this would be tension, and this would be tension. And the extra marks come from the fact that you don't put the weights in because they only wanted the horizontal forces. So that was what, and that you didn't put anything in acting backwards because it was a frictionless plane. Calculate the horizontal force acting on the 3 kilogram block. So it's a resultant horizontal. So it's going to land up over here where you're going to say 3 times 1,5 and you land up with 4,5 newtons. That's the resultant force. And what would happen if the blocks were just left? There'd be no unbalanced forces and they would continue in the same state of motion.